Welcome to this last video in this series on functions. And that's because we have reached the real functions, which is the most powerful class of functions within the scope of this series. There are also complex functions, and you can do complex analysis on those, and that's amazing. It's such a beautiful mathematical discipline that I really recommend you take a course on at university, for example. It's slightly abstract and more complicated than what we're doing right now, but it's really beautiful and powerful. Within this context, however, we're going to look at three main characteristics in this video. We're going to be looking at the area under the graph of a real function. We're going to look at continuity, or the connectedness of the graph, and then we're going to be looking at the slope of the graph. These have also mathematical names, but we'll get to that once we reach that portion of the video. All right, so let's start with a nice little function, f. As always, it goes from some interval ab into some other interval. All right, so between two intervals, and a and b can be infinite. Either of them can be infinite or neither or whatever. Just the important part here is that these are some intervals. They can also be open if we don't want to include the endpoints, but yeah, it's most of the analysis is pretty similar, barring some technical details. All right. So let's draw the graph of this function. I haven't given you a functional expression, so I don't really know what it looks like. So I'm just going to come up with something. So we're going to have the interval here, a, b, c, and d. All right. So let's make a function. And continue it up here, something like this. Isn't that a beautiful function? And just for good measure, let's make a circle here. And the circle just means that this point is not related to the corresponding value, so this is omitted and this is included. So the value at this line, this vertical line here, where these circles are the same vertical line, we include this value and not this value. All right. I'm going to start with the area under the graph, and the reason I'm going to start with the area under the graph is because there's no issue with calculating the area under the graph of this function, even though you can see it's clearly disconnected. Okay. And how do we define the area under the graph? Well, it's pretty relatively simple. We simply calculate this area between the function and the x-axis, where we assume that this is the x-axis. If it's not, we just go further down. All right. How do we do that? How do we calculate this area? It's not immediately obvious. One thing I'm going to start doing to make the analysis slightly easier is I'm actually not going to consider this as one case, because it's slightly problematic. With other constructs, you can definitely do that. But what I can do here is I can simply look at this part of the graph, calculate the area, and then look at this part. And we will avoid this problem area here. So you can totally do it, but it's more convenient just to take the connected areas of the graph and treat them separately. Okay? So let's just imagine that our function only goes to here. So we're just focusing on this part. Okay. Well, how do I calculate this area? Well, one construction you can make slightly naively, and there are other better ways to do this, more robust ways to do this. But let's just create some intervals here. So I divide this into two intervals. I make a division of this interval into sub-intervals. All right. And I do this once. Well, I can start by doing this once. And then I can, for example, I can make a rectangle here. Let's make a rectangle here. Let's make a rectangle here. So you can see I've made two rectangles here. And I've tried to, actually, this one is a bad rectangle. I mean, you can use it definitely, but I just wanted to be a little bit nicer. Okay. So now I made these two rectangles. And what my goal here was to have each of these rectangles kind of estimate the area under the graph. And you can see, hopefully you can see, I have kind of achieved that. So this part, I'm missing this part, but I have a little bit over here. So the area under the rectangle, area of the rectangle is probably going to be approximately the area of the graph. Same over here, the area that I'm overshooting here is roughly the same as the area that I'm undershooting here. So the area of these two rectangles is probably pretty close to the real thing. But probably pretty close is not very satisfactory to most mathematicians. Okay, so let's see if we can do this. We can do this a little bit better. So let's make a second division. So we subdivide these intervals into this thing and this thing. And then instead of this, maybe what I do is this is still this rectangle, but let's make it over here and over here, something like that. And over here we do something like this, and then something like this, right? And you can see we're slowly approaching something that's closer to the real area. And what we actually do is we just make an infinite number of subintervals here, and then what's going to happen is the area is simply going to be precisely the same as the area under the graph. The errors are going to become infinitely small, and what we're going to end up with is this same thing in the limit. All right. You don't have to make these intervals this nicely. You don't have to make them like cut it in half every time. You can make any sort of interval. The important part is just that every single interval needs to become infinitely small in some systematic way. I'm not going to go into details what that means. But what we have here is, so the area under the graph from A to B is denoted with an old-timey S. And the way it's written is like this. So this is an old-timey S. If you read old Latin text, a lot of the S's are going to look like this. And we go, okay, so the area from A to B, like this, is going to be this of this function. The f of x, where we put the functional expression in here, and then we write d of x. And the d of x is just the delimiter. So it just goes, okay, this is the end of our function, but it also serves another purpose. And the other purpose is to tell us, well, this is our variable. Because we can technically have f that's a function of several variables. And it's important to tell the function, okay, which variable am I looking at right now? So that's the two purposes of this dx here. So this is the notation for the area under the graph. Beautiful. Yes, there is a slightly stringent, not the most stringent, way to actually calculate this. And the way you do that is you go, okay, this is the limes of the sum of all the areas of all these rectangles. And the way I calculate the area of a rectangle, well, I take the base, and that's going to be delta xk, and then f of tk, where k goes from 0 to n. And then I have n approach infinity. So what I've done here is, okay, I've said a is x0, this one is x1, and then I go up to xn, and I actually call xn plus 1. That's what I call the xn plus 1. So I have let me give this. Yes, beautiful. So so what I've done here is I've taken the width of each of these intervals, the difference between this and this, which is this delta here, and then I've multiplied by the function value at some number, where tk is in the interval. So we have the interval from tk to, xk plus 1, and then tk is some value in there. I've chosen it to be nice here, but it really doesn't matter. The important part is just that it's in the interval somewhere. So this is the most rigorous definition of the integral, mathematical definition of the integral that you will get for now. All right. I've not specified how you do this limit or this limus, but it just means that we have the intervals, the number of intervals we have that approach infinity, but it's actually also slightly important that we do it in a specific way. So there's a lot of details that I've omitted here that you will work more with at university, I'm assuming. All right, so this is the area under the graph. The next characteristic that I'm going to be looking at is I'm going to be looking at continuity. And as you can tell, I chose this function because it's actually not continuous. It's not connected. There's a big portion of this graph that is simply not connected. And how did it look? It doesn't really matter, but something like this. All right. So how do we define continuity? Well, just intuitively, it's simply this fact that it's not connected. So it's connectedness, at least in 2 dimensions like this. And how do I define that more rigorously? Well, here we have this beautiful thing called an Epsilon-Delta definition. And the way that works is the function f is continuous at a point if for all delta larger than 0, this means for all, there exists an epsilon larger than 0 such that if x is at most epsilon delta distance away from our point, then the function values are also pretty close to each other. This looks super technical, and it really is. You don't have to think about it too much. What it's really saying is, let's say I choose some delta larger than 0, and I want to check the continuity at this point. Okay? So I have f of x here, x0 actually. All right? And let's say I have a delta. Let's say I can take a delta, and this here, this is delta. This distance here is delta. All right? Then this says that I can always find an epsilon such that if the distance in the domain is smaller than the epsilon, then the function values will also be less than delta. But hopefully you can see how this breaks, because it doesn't matter how close to this point I get. It doesn't matter how close to x0 I get. I will always find values that are outside this band. You can see here. Because regardless of how small I make this interval here, I will always find function values that are down here outside this interval. So that's what this definition says. It simply says that I can, for each of these bands, I can find a small band in here where all the function values are within this band. And it breaks exactly at these discontinuous points. So even though this may feel abstract, it's just a mathematical description of these discontinuities. And it can be an exercise for the viewer to actually check that if I put this band somewhere else, you can actually do this. You can create this epsilon band down here that ensures that they're close enough together. So this is continuity. And the last part will be the slope of the function. And the slope of a function is called the derivative in mathematical terms. And the way this works is, let's say I want to find the derivative at some point here. Let's say I want to find the derivative at this point. How can I do that? Or the slope, rather. Okay? If this was a linear function, it would be easy. I would just take the rise over run, right? But you can't do that here because the slope is constantly changing. All right? But I still get inspired from linear functions. So what I do is I take another point, just arbitrary point over here, and then I have a line, and I can calculate the slope of this line, right, with rise over run. So what I can do here is I can calculate the slope here as rise over run. But this is not the exact same slope as the slope of the function. Just like with our the area under the graph, it was just an approximation, and you can see this is an approximation. It's actually a really bad approximation because this slope is way off compared to this one. What we can do here is we can halve this distance, half it again, and you see the slope will slowly become better and better. And as soon as we actually get infinitely close, just like we need an infinite number of intervals for the area, if we get infinitely close to this point, what we actually get is we get the slope at that point. And and these lines here, where we have 2 points, are called secants, I hope. But as these 2 points coincide, they stop being a secant because we just have 1 point. We're just intersecting the graph at 1 point, and we have a tangent. So what we're looking for is the slope of this tangent line here. But what we start with is the slope of the secant line. And then what we do is we can calculate this as f of x 2 minus f of x1 divided by x2 minus x1. We're not actually not interested in the second point. That doesn't matter at all. Or the first point for that matter. We're just interested in the slope at the one point, the other point, which is an arbitrary point. So it doesn't really make sense for us to have 2 points in this. All right. So what I'm going to do is I'm going to replace this change in the difference between these two values by some number h. So I'm going to express this as the 1 point, and then the other point I'm going to express as its distance from the first point. Okay. So I'm going to write this as f of x plus h, the distance between the 2 points, minus f of x. And then I'm going to write just h here, the distance between the 2 points. So this is my secant line, whatever. All right. And then the mathematical definition for the slope is then going to be the limit as h becomes smaller and smaller. Just like the limit up here, now it's just going to be, so the derivative or the slope of the function at some point is going to be the limes for h going to 0 of the secant slope. Isn't that beautiful? All this was only possible because our domain started being these nice mathematical objects that allowed us to do all these crazy fancy manipulations. Namely these beautiful continuous intervals where this is possible. All right. How the hell do I remember that? This is the struggle for a lot of students to actually remember this. The way I remember this is I use something similar to the Danish school system where they use the 3-step rule. And the 3-step rule in the Danish school system is you express the secant slope, you reduce it, and then you take the limit at the very end. These are the 3 steps. But personally, I prefer calculating only this difference. Because a lot of the reductions only happen in the numerator without the denominator. And if you want to do this first, you're going to end up with a lot of calculations. So this is my first step. And then the second step is, well, I take this and I divide by the h. And then I reduce again. So after every step, I reduce my expression, rewrite it if necessary or possible. And then the third step is having h approach 0. So you so you have this expression as h approaches 0. And at this point, you may need to use some tricks or previous results or whatever. But this will be my 3-step rule, because in practice, this is the way I usually do it, and not the other way around. Yes, that's all the time I have for now, and this will actually be the last result in this section. Check out my section on integrals where I actually connect the derivatives to the integrals. Question, comment? Down below.